Now we are going to see about how we are going to represent the floating point numbers in a standard IEEE format. So this is the given procedure how we are going to convert the floating point numbers into a IEEE standard format. So the first step is we are going to convert the given decimal numbers into binary, and then we are going to combine both the fractional part and the integer part. So this is the first step, and in second step we are going to represent it in the exponent form, that is a scientific notation. So with the exponent we are going to represent the already converted decimal value. Then the next step, that is the third step, is we are going to calculate the single precision. So for single precision we have to calculate what is the sign bit, what is the exponent, and what is the mantissa. And the step 4 we are going to calculate for the double precision. So in double precision also we are going to calculate the sign bit, exponent, and mantissa. Let us take the example, that is we are going to express the value that is minus 0.75 in IEEE 754 format, and we are going to calculate the single and double precision. So let us see how we are going to convert the value into single and double precision by using the IEEE format. So step 1, we are going to convert the decimal to binary, and then we are going to combine the fractional and integer part. Okay, so the solution, first we are going to see the step 1. So step 1, so what the value is, we are going to take the value of minus 0.75. For 0.75 we have to convert this into binary values. For 0 it is the integer part, there is no need to convert the binary value because it is a in 0 format. So just we are going to calculate for 0.75. So for 0.75 we have to take this value and we are going to multiply by it too. So what the value we are going to get, so the value we are getting is 0.75 into 2 will be, it is 1.5. Okay, so now we are going to take only the integer part. Okay, so this integer part we are going to take, that is a 1. Again what we are going to do, again we are going to consider this value, this integer as 0, and just we are going to take only 0.5 into 2 again. So the value will be, it is 1.0. Again we are going to take the value, the first integer part, that is 1. So now again we have to take this value, right, that is 0.0 into 2. So this will be 0. So after this we cannot find the value of the floating point number. So this is the value, or this is the method to calculate the floating point numbers, that is after the for the fractional part, this is the method we are going to calculate. So the value we are having is 1 and 1. So we are just going to represent it as, we are going to combine the value, so it is minus 0.11. So this is what the first step is. The next step is we are going to calculate the scientific notation. So scientific notation is nothing but we are going to represent it in the exponent form. Okay, so for these value only, the fractional value only, we are going to represent it in the exponent form. So 1 and 1. So the binary values are represented in the base of 2. So after radix point we are having, after radix point we are having the two values, but before the radix point we are not having any value. So that is considered to be the exponent value. So here the exponent value will be 0. In floating point representation we have to represent it in a normalized way. Okay, so here we are not having any values before the radix point, so we are keeping the exponent value as 0. For example, if we are having the value like 100.001 means we have to make it in a normalized way. So in normalized way we can say we have to move the radix points towards the two places before the value. Okay, so now we can say it is a 1.00001. So we are going to move the value 2 points before. Okay, so that is called as, and that value will be represented into 2 power plus 2. So this is the exponent value of this 100.001. So this is how we are going to express the exponent value. So step 3, we are going to calculate for the single precision. Okay, so single precision, we know that The format is for single precision we are having, that is 1-bit sine field and 8-bit exponent and 23-bit mantissa field. So this is what we are going to represent. So sine bit, the value we have taken is minus 0.75, in which we have calculated the binary value is 0.11 into 2 power 0. This is what the value we have got in step 2. Okay, so this is a negative number. So negative number we can represent by means of, so we have to calculate three values. That is, first one is the sine bit. So sine bit is 1 because it is a negative number, so the value is 1. Then the next one is the exponent. So exponent, what we are having, the exponent value is 0, but by default we are having the bias exponent. Okay, so bias exponent we are having, the bias value will be 127. Okay, so for 127 we have to calculate the binary LCM method. Okay, so if we take LCM method, means we are going to get the value, that is 7 1 2 3 4 5 6 7, and if it is a 8 bit, I am going to represent by means of using one single bit 0. Okay, then the next value is the, we are going to calculate the mantissa part or significant. So mantissa value is nothing but it is the fractional part. So fractional part we are having 1 and 1. So we have to represent it in the 23 bit. Okay, so 23 bit means, so this is 3 bit, then extra 20 bits we have to add. So 1 2 3 4 and 5. So this is how, that is a 5 4 20, 20 plus 3, 23 bit we have added with the mantissa part. So now we have to combine all these values. That is 1 and 8 bit is 0 1 1 2 3 4 5 6 7, and remaining is the 1 1 0 1 2 1 2 3 4 and 5. So this is the single bit precision value. Now we are going to calculate for the step 4. Okay, so step 4, so step 4 is nothing but we are going to calculate for double precision. So for double precision, the format will be of, so it is the 1-bit sine field and 11 exponent and 52-bit mantissa part. Okay, so this is what the format is. So again we are going to calculate the sine bit value. So the sine bit, which is equal to 1, and again the exponent is for single precision, for that is for the 32-bit, it is the value is 127, and now for double precision, that is for 64-bit, it will be 1023, the value will be. Okay, so our exponent is 0, so 0 minus 123. So for 1023 we are going to take the LCM. So if we take LCM, means we are going to get the value, that is 11 1, binary value 11 values we are going to get the 1 1 2 3 4 5 6 7 8 9 10 11. Sorry, it is a 10-bit value, so before 1 I'm going to add the value 0. So this is what the exponent is, and the last step is that we are going to calculate the mantissa. So mantissa is nothing but it is 0.11, so it will be represented into 52 bits, so 110. So all the remaining things will be of 0, so it will continue. So just we are going to combine everything, so it is 1 0 and 10 1 1 2 3 4 5 6 7 8 9 10, and the next one is the remaining mantissa part. So this is how we are going to calculate the double precision.